What's up guys, Major Math with another video on fluid mechanics. If you have any questions, drop it in the comments, and if you're having trouble with other problems, I've attached my email in the description, so please feel free to reach out. Without further ado, let's get started. Question 3.82 in the textbook says, two water manometers are connected to a tank of air. One leg of the manometer is open to 100 kilopascals pressure, while the other leg is subjected to 90 kilopascals. Find the difference in deflection between both manometers. Deflection is just the difference between these heights, right? Okay, so we're going to have to definitely use a manometer equation, but first things first, let's figure out our goal. Our goal is to find, kind of list it out for us, the deflection, right? The differences in heights. Our givens, whoa, that looks weird. Our givens is this pressure. It gives us this pressure, the atmospheric pressure. It says 90 kilopascals, right? Yeah, 90 kilopascals on the left leg and 100 kilopascals on the right leg. And that's all it gives us, okay? So when dealing with manometers like this and finding deflection, most likely going to want to use this equation, right? Manometer equation. Usually anytime a manometer is involved, you will use the manometer equation. And let me pull up the textbook. The manometer equation looks like this. Yeah, right here. Table F.2. So it says pressure 2 equals pressure 1 plus summation of everything going down. I'll explain this a little bit. Okay, so I'll show you guys how to use this manometer equation. So see these little subscripts, we're going to have to label our diagram to know what we're working with here. So we're going to label this point, we're going to say this equals P1. We're going to say that this equals P3, and that the pressure in the air equals P2. Okay? So we're going to kind of work our way around. We're going to have to do the manometer equation twice to find pressure 1 or pressure 2, and then use it again to find this deflection. Okay, so well, actually, I said that wrong. We'll use the manometer equation to find the pressure at point 2, and then we'll use the hydrostatic equation to find the height difference. Okay, so let's see how we use this. So we got our pressure at point 2, which we're trying to find. We have this, and we know specific weight of water if we assume, say, temperature equals 10 degrees Celsius. We can get that value from the textbook. And then the heights we also do not know, correct? Yeah, but we can set up an equation for pressure 2 to equal the difference of heights, and then use that hydrostatic equation to solve. So we'll see what we're doing here. Okay, so down, so we're working from pressure 1 to pressure 2. So move down, and then from here we move up, right? So we're going to say pressure 2 equals, and up is negative because you lose pressure. That will be of water, and the height is this change at point A, okay? So our first one. So that's how we're going to do right there. We're going to go to the other leg and derive another equation for pressure 2. So let's say pressure 2 equals pressure 3 plus down up. Okay, so we're working from pressure 3 to pressure 2. We see we go down, that's atmospheric, so we don't count that. And then we move up this distance of HB. So pressure 2 will equal, we're only moving up to get to air. So all we do is put pressure 2 equals pressure 3. Oh, and I forgot to put pressure 1 over here. Yeah, that gives us pressure 1. Pressure 3 plus minus the void of water times the height, which we don't know the height yet, but it's HB. Okay. So we just found two different equations to solve for pressure 2. So we can say that these are equal to each other, right? So we know that pressure 3 minus HB equals pressure 1 minus physical weight. Okay. So we know this value, we know this value, we know this value, but we don't know the height values, right? So we can solve for that deflection by doing this right here, rearranging. If you rearrange, you can get to the point that looks like this. So I was stood correct. We do not use the hydrostatic equation, but you can see what I'm doing here. So doing some rearranging this equation, we can get it to have this on one side and the rest on the other. So now we can see how we can actually solve for that deflection difference. So we plug in everything we know. You know that P1 is 90 kilopascals, which is also 90,000 newtons per meter squared. Pressure 3 is 100 kilopascals, which is also 100,000 pascals, which is also 100,000 newtons per meter squared. Put that over the specific weight of water. From the textbook, if we're assuming the temperature is 10 degrees Celsius, it says 9810 is the specific weight, newtons per meter cubed, and that will equal the deflection. If you put that in a calculator, you will get 1.02. You actually get negative, but so that's the height difference, the deflection difference, and all that negative number means is that the height of H at point B is much larger at the height than HA. So we say the deflection difference, deflection between the two heights is 1.02 meters. Thanks for watching, soldiers. Don't forget to leave a like and subscribe for more content like this. If you have any questions, leave it in the comments, and if you need help with any other problems, feel free to contact me with the email shown on the screen.